Hey everybody, in this video we're taking a look at how to manipulate equations to solve for a variable. I find that a lot of times when students get to the advanced physics or AP physics level, they're pretty comfortable with algebra and order of operations and kind of that basics, but they're less comfortable or less used to keeping equations in terms of all of the variables that are already in it and then solving for another variable. So in this video we're going to take a look at that. How do we solve for a variable in an equation, keeping everything in terms of the variables that are already in there. So let's just jump in and take a look at what I'm talking about here. Here's our first example. It says solve for omega. Looks like a W. It's actually the Greek letter omega. Stands for angular velocity, but we're not interested in that right now. We're just taking a look at the algebra side of this at the moment. So we're solving for omega. We've got our equation there, k equals 1/2 I omega squared. So the first thing that we're going to do is multiply by 2 on both sides. We want to get rid of that 1/2. So when we do that, we get I omega squared equals 2k. You can also see that I switched the two sides. I put the I omega squared on the left and I moved the 2k to the right. Since I'm solving for omega, I personally just like having the variable I'm solving for on the left side. So a lot of times I'll switch it to get that where I want it to be early on. Next, we're going to divide by I on both sides. So divide by I right here, divide by I right there, and we get omega squared equals 2k over I. And then we're just going to take the square root of both sides. And we get omega equals square root of 2k over I. And that's our final answer there. So pretty straightforward there. We're just using the regular inverse operations we would use to solve for a variable. We just don't have any numbers in there. Everything is still in variables or constants. Here's our second example. It says solve for theta in terms of W. And so we have the work equation here, but again, we're not worried about the physics of this really. And this one's kind of weird. We've got two equal signs in there. Also, by the way, all of these equations I'm using are taken from the AP Physics 1 equation sheet. So these are how they're written on the equation sheet. So we have W equals F. This means parallel. There's parallel and perpendicular. This is the parallel sign. So this force parallel times D, which is a distance, equals FD cosine theta. So it's kind of like this W equals this, but it also equals this. So what are we going to use here? Well, let's take a look at what we're trying to solve for. It says solve for theta in terms of W. Well, we've got W right here. We've got theta right there. This middle part, it says F times D. There's no theta or W there, so we're really not interested in that at all. So I'm going to rewrite this and not include that middle section of our equation. We're solving for theta in terms of W. All right, so FD cosine theta equals W. And again, I switch these around the equal sign because I'm solving for theta. I want my theta to be on the left side. So FD cosine theta equals W. Next thing, we're going to divide by FD on both sides, and we get cosine theta equals W over FD. I'm not going to show every little operation that I do on here, so I'm leaving out some of those. But at the same time, you want to be able to follow my work really closely. And so I'm going to try to show every step here. Remember, on the AP exam, you're not just getting a right answer, you're showing your process, showing your work. That's something that's important whenever this is being graded by especially in the free response, when this is being graded by the AP graders, they need to be able to see your process. Next step, we've got cosine theta, but we need theta by itself. And so now we need to use the inverse operation of cosine, which is inverse cosine. So we're going to take inverse cosine on the left side. Same thing on the right side. I don't have to rewrite this, so I have a little bit more room. Inverse cosine of W over FD. And whenever we do inverse cosine of cosine, those are going to cancel out, and we're just left with what's in the cosine, which is going to be theta. So we end up with theta equals inverse cosine of W over FD. And that's our final answer. We solved for theta in terms of W. It's also in terms of F and D, but we do have it in terms of W. So we're good with our answer there. Here's our third example. We're solving for R from this force of gravity equation. I'm using this as my third example because it's going to illustrate a common mistake that I see students make whenever they're solving for a variable that's in the denominator. We're solving for R, which is in the denominator of that fraction right here. So first thing, I'm going to get rid of, and we kind of saw it disappear there real quick. I'm going to get rid of the absolute value sign right there. That absolute value sign means magnitude. Magnitude is just like the amount of something, not the direction. We'll get into that when we get into the physics later on. And also this arrow above the FG is referring to the fact that this is a vector, that it has a direction. So we're just going to get rid of that because we're really just wanting this in terms of R. We're going to ignore that rest of that stuff. Next thing, that capital G, when we multiply this out, it's actually just going to end up on the numerator with the M1 and the M2. So I'm going to write it like that just to kind of simplify this for us. FG equals G, M1, M2 over R squared. Now there's a couple ways to go about solving this. Here's a common one that I see students do. They know they need to isolate the R, and they've got this G, M1, M2 on the top. So they're going to divide both sides by g m1, m2. They divide that on the right side, they got to divide that on the left side, and they're going to have the g m1, m2 here, cancel out the g m1, m2 there. And so they'll rewrite it like this: f sub g over g m1, m2 equals r squared. And that makes sense because, right, we got rid of this. All we're left with is the r squared. But that's a huge misconception that I see students make. We're not left with r squared. R squared is in the denominator. We're left with 1 over r squared. So just be careful when you've got a variable in the denominator that if you do something like this, you're left with 1 over that variable, not just that variable. So I'll rewrite that. This is be correct now. So we end up with this. We're trying to solve for r squared. There's a couple ways to go about it now. We could multiply it by r squared on both sides, and then divide by fg on both sides, and then multiply by g m1, m2 on both sides, and we'll get our answer there. Another thing that we could do, because we just have a fraction on the left, a fraction on the right, we can take the reciprocal of both sides. So take the reciprocal of both sides, and we're going to get r squared. It will be r squared over 1, which is just r squared, equals g m1, m2 over fg. And then we'll take the square root of both sides, and we get r equals square root of g m1, m2 over fg. So that's one way to do it. I think there's actually a better way to do it. I'm going to show you the same problem again. This is how I would approach it, I think. So go back to this point right here. We're trying to solve for r squared. My recommendation would be to get the r squared into the numerator or out of the denominator as early as possible. Just do that at the beginning, and then you don't have to worry about that misconception or that mistake that I showed earlier. So let's take this and let's go ahead and multiply by r squared on both sides. And then we're left with r squared fg equals g m1, m2. And then from there, it's going to be easy. We're good to go from here. We don't have anything in a denominator that we're solving for, and we can just follow the steps from there. Divide by f sub g on both sides, we get this. Then take the square root of both sides, and we get r equals square root of g m1, m2 over fg. Awesome, so we've gone through 3 examples of solving for a variable in an equation. We looked at a trig function, we looked at something in the denominator. Now let's take a look at the hardest problem of this video so far. And in this one, we're solving a system of physics equations for a particular variable. Now I'm sure you've done systems of equations in Algebra 1. This is gonna look a little bit different though. It's mostly a lot of substituting in, but again, we don't have any numbers that we're substituting in here. We're gonna substitute one equation into another. So let's take a look at this. Use the equations below to solve for P in terms of A, delta x, and m, given that V sub 0, that's initial velocity, equals 0, and x sub 0, that's initial position, equals 0. But again, if you don't know what any of these variables actually mean, that's totally fine. We're just looking at the algebra right now. If you are curious, this is the definition of momentum equation, the position equation, and a velocity equation. We're solving for P in terms of A, delta x, and m, and it tells us that V initial and x initial equals 0. So we can go through these equations and go ahead and basically cross out the terms that are going to be equal to 0. So in this case, x sub 0 is going to be equal to 0 plus the rest of this stuff. We'll just be able to ignore that part. Also, this x right here and the V sub x 0, that just means we're looking in the horizontal or x plane, x direction. So we're kind of just going to ignore that. Sometimes that might be a y if we're looking at vertical velocity and position, but not of interest to us in this particular problem. That term is going to be 0 as well because V sub 0 is 0, and so V times t is going to be 0 then. So that term was going to go to 0. And then finally, in that last equation, we've got another V sub 0 that's going to become 0. This is not going to become 0 because that's not V initial, that's just V. So we have to keep that as it is. Now that we've done that, let's rewrite these equations. So x equals 1/2 at squared. I'm just going to ignore that x because, again, that's just telling it's in the horizontal direction for that acceleration. And we'll rewrite the other one, v equals at. Great, now we're solving for p. We've got p equals mv. So we already have this equation how we want it as far as it's p equals something. But we want our equation in terms of a, delta x, and m. So looking at our equation here, we've got m, we're good with that because we said we want it in terms of m. But we've got v, we didn't say we want it in terms of v, we want it in terms of these other variables, a and delta x. So we're going to have to substitute something in for v. Now I've got an equation that's already written as v equals. So we can take that equation and we can substitute that in for v right here. Great, so now we're going to have p equals m at. We substituted the at in for v because we know that v equals at. So at this point we have p equals m at. Let's check and see how we're doing so far. We have m, great, we're trying to get this in terms of m. We've got a, we're trying to get that in terms of a. And we have t, we're not trying to get this in terms of t, we're trying to get this in terms of delta x. So we've got to substitute something in for that t. Now we've got an equation still with t in it. That's that middle equation right here. So we want to rearrange that equation to make it t equals. So we're just going to follow a similar procedure like we did in the previous problems in this video. We're going to solve that for t. So we'll multiply by 2 on both sides, and we'll get 2x equals at squared. 2 times 1/2 gives us 1, so we're left with that. Then we're going to divide by a, so 2x over a gives us t squared. Then we're going to take the square root of both sides, and we'll get t equals square root of 2x over a. And now we can take that, because we've got it as t equals, and we can substitute that square root of 2x over a in for the t in our equation here. All right, that's going to leave us with this. P equals ma square root of 2x over a. And now we have it how we want it. We've got it in terms of m, in terms of a, and in terms of x. So we're good there. Also, I just realized I left this as delta x. In this case, because x initial equals 0, and delta x means the change in x, delta x and x in this problem would be the same thing. So my mistake on there. So this would be a final answer. We've got what we were asked to. We can simplify it a little bit more. So let's go ahead and simplify it the rest of the way, although what we have right here has answered the problem. But we've got a and then square root of a on the bottom of that fraction over there. So we can simplify this a little bit better. So let's take this and rewrite it. P equals ma times square root of 2x over square root of a. Remember, if you've got the square root of a fraction, you can split that up into square root of the top over square root of the bottom. And now we have a divided by square root of a. And if you remember your rules for division of square roots and all of that, something over square root of that same thing is just going to be square root of that thing. So a over square root of a is the same as square root of a. So we can now rewrite this as m times square root of a times square root of 2x. And then we can put all of that under the same radical, and so we get p equals m times square root of 2ax. All right, this problem had a lot going on with it, but here's the kind of the main idea of it. We're solving for a particular variable, and we have multiple equations here, and we want that variable in terms of some other variables. Now, why do we want that? Well, it just depends on the physics problem that we're trying to solve. Maybe in this case, we're trying to solve for the momentum p, and we know information about acceleration and position and mass, but we don't know anything about the time that something took, and we don't know anything about the velocity or average velocity that the thing had. So we want to rearrange this because of the information that we know in the problem. So we're trying to solve for a particular variable in terms of certain other variables. So we'll take the equation that has that variable in it, and then we'll start substituting in for any other variables that we don't want to have in our equation. So in this case, we substituted in for the v, and then we substituted in for t, and sometimes you've got to rearrange the equation to get the variable that you want, that you're subbing in for. And it's kind of like a puzzle, but our end result here is that we have an equation that's in terms of the correct variables that we're looking for. All right, that's it for this video. Good luck with manipulating equations and solving some physics problems. All right, bye.